All right.
Oh, they drove yesterday?
And Hannah Brandt needs to report to the cafeteria.
All right. So let's see. We got to finish up with chapter 13, and then we can move on to chapter 14. So this is where we left off yesterday. I just want to show you. I didn't get to this part, but the different forces that are acting on wind at the surface and up in the air, which I don't. Maybe I don't fully understand the up in the air one, or maybe it's wrong. I don't know. But you can see high pressure down at the bottom of the picture, low pressure at the top. So your wind wants to go directly from the high to low, which is the red arrow here. But it has two other forces acting on it. It has the Coriolis effect, which makes it want to deflect off to the right. And it also has friction because of the surface of the land, which is going to kind of slow it down and pull it in the opposite direction. And so if you add all three of these vector arrows together, your wind actually deflects off just a little bit to the right as it blows. So it's still going to go from the high towards the low, but it's going to be deflected a little bit. Up in the atmosphere, where there's only the Coriolis effect and the pressure gradient force going from high to low, your wind is going to deflect almost 90 degrees to the right, which I'm not, I don't know that that's the most accurate representation, because my question is, if the Coriolis effect is acting in the opposite direction of the actual pressure gradient here, it doesn't seem like your wind would go to the right. It would just slow down. If we're talking about like vector forces. So I don't know that that's 100% correct. And why would the wind just go to the right? If it's only going to the right, you're not really having any transfer of wind go from high pressure to low pressure. So you're not alleviating any of those pressure differences. So that one might be a little bit suspect. I'll have to see if I can figure out how to explain that. But as we move forward, they talk about upper air winds, which are jet streams. The Gulf Stream. Gulf Stream's a plane. Is it also a weather thing? Now I'm questioning myself. But anyways, the Gulf Stream, the Gulf Airstream is what brings us a lot of our weather, and that is a type of jet stream. They tell us that the jet streams kind of run parallel to the isobars, and so it's going to run along these lines down here, down through the Gulf, and kind of bring us different weather packages. So this just shows you where some of the jet streams are taking place. Briefly describe the Coriolis effect and how it influences air. Basically, it's going to deflect air in the northern hemisphere to the right and to the left in the southern hemisphere because of the way the Earth rotates and how the air has to compensate for that. So now we get into cyclones. Cyclones, when we think cyclones, our brains, because we're from Texas, think like tornadoes or like little dirt devils. That's not what they mean when they mean weather cyclones. Weather cyclones are huge low pressure systems. They do have that rotation. So there's always going to be a rotation with the cyclone, but it's over a very large area and it's centered around a low pressure system. So if you have that L on the weather map for low pressure, you're going to have all your weather kind of circulating around that. In the northern hemisphere, it's counterclockwise. In the southern hemisphere, it goes the opposite direction. It's clockwise. They're both going to go inward because it's still low pressure. So air wants to go from high pressure to low pressure. So the winds are going to be blowing inwards towards the center of the low pressure system. But in the northern hemisphere, they spin counterclockwise. In the southern hemisphere, they spin clockwise. Your cyclones and your low pressure is usually going to bring rain and thunderstorms. Where the opposite is true for your high pressure systems, which we call anticyclones. They're going to bring fair weather, clear skies, and usually warmer temperatures. So if you have rain happening somewhere around you, it's because there's a low pressure system coming in, which is bringing a cold front. In fact, I think we got one coming through today. We got not high chances of rain, but there's like a 30-40% chance of rain, I think, at least. And tonight, the temperature is going to be colder than they were this morning. This morning wasn't that bad. It's like in the 40s. Tomorrow morning, I don't think it's going to get down to freezing, but it'll be in the 30s for sure. So we got a cold front coming through because we got a low pressure system kind of passing by. In the summer, when there's no rain and it's just hot weather all the time, usually there's a high pressure system sitting right over Texas, and we're not getting any kind of differences in air mass. But you notice high pressure system, all the air is headed away from the high pressure system and it's spinning clockwise. The low pressure system, all the air is heading in towards the low and it's spinning counterclockwise. So they're kind of flip sides of the same coin, which is why we call them cyclones and anticyclones. Here's a picture of two cyclones. Not one of these is not an anticyclone. They're both cyclones. They're just different hemispheres. So northern hemisphere, your cyclone's going to spin counterclockwise, and you can see all the wind headed in towards the center. And the southern hemisphere, the same thing's going to happen, but it's going to spin clockwise instead because it's in the southern hemisphere. These do look like hurricanes from the top. It's not necessarily a hurricane. Hurricanes are low pressure systems, but the cyclones that we're talking about are different from your actual hurricane storms. So an anticyclone is going to be the opposite. In the northern hemisphere, it's going to spin clockwise. The winds are going to blow outward because it's high pressure. It's going to move everything out. You usually don't have very much bad weather with this. It's fair weather, warmer temperatures, clear skies usually. And so high pressure systems are kind of associated with all that. Here's a three-dimensional kind of map showing you all the air headed in towards the low pressure system. And in 3 dimensions, it kind of gets a little trickier because if everything's headed in towards this spot of the low, where's all that air going to go? It can't just stay there because the more air you pack into one area, your pressure is going to go up. So how do we keep low pressure here with all the air coming in? It's got to go up. And so above a low pressure system, your air is rising, where when it gets to the top of the atmosphere, it's got to go somewhere. It starts to spread, which is the opposite of what it's doing on the surface. Same thing with the high pressure. High pressure, all the air is moving outward. Well, I got to have air to replace the air that's leaving. So it's going to come down from the top of the atmosphere and kind of fill that back in. So it's like this big cycle of air that's happening from the surface all the way up to the top of the atmosphere. And we'll see different pictures like that throughout the PowerPoint. So what causes this stuff to happen?
The following students need to report to the cafeteria. Andreas Adame, Lizzie Nicole, Giselle Alejandro, Jonathan Alvarado, Lindsay Baker, Cameron Bates, Mark Gordon, Nadia Bryant, Brianna Castillo, Juan Castillo, Alexis Chavez.
Come on, you know it ain't Castillo. Castillo, jeez. All right. So what causes high pressure and low pressure systems? Unequal surface heating. If one area is hotter than the other area, your hotter area is going to have higher pressure, and it's going to flow towards your low pressure area to try to equalize that out. Now, there are some areas that aren't necessarily subject to moving high and low pressures. They kind of have general high and low pressures. So the equator mostly has low pressures all year round, which is why they have similar weather patterns all year round. The subtropics usually have high pressure systems, and we can see that on the next map. There's a lot going on these maps. You can see the equatorial low, so air is always moving in towards the equator. You can see the subtropical highs, so air is always kind of moving away from that subtropical high because of the high pressure. And you can see why we have a lot of rain around the equator is because this warm air comes in towards the equator. It has nowhere else to go, so it goes up. And as it goes up, it cools and starts to drop rain. So that's why we have rain bands mostly around the equator. So there's a lot of complexity here with the different cells going up and down in the atmosphere, the different movements along the surface. We have another generalized version over here. And so there's a lot to learn, and weather's very, very complex. And the people who study it and tell us about the weather usually make decent paychecks. So if you're interested in science and you're like, hey, I'd like to be a weather person on the news, you can probably be that, because I like our weather people, but if you ever like go on a trip somewhere and watch the news in the morning, sometimes you're like, almost anybody can be a weather person. These people are not very good at TV jobs. So if you have like some science aptitude and the ability to speak in public, that can get you on the news as a weather person. So, influence of continents is going to be greatest in the northern hemisphere because we have the most continents. In the southern hemisphere, they're there. They're just not. They don't cover as much area in the southern hemisphere. So, global pressure patterns and wind patterns change depending on what the continents are doing. Are the continents hot? Are they cold? And different times of the year, that's going to affect your weather. Monsoons are going to be heavy rain seasons. Generally in the summer, you get a lot of warm, moist air from the ocean, and that's going to give you long periods of intense rain. And so there's different parts of the country that have monsoons. We don't really get a lot of monsoon seasons in the United States. These two maps are actually pretty complex. They show you the difference between January weather and July weather. So for the northern hemisphere where we live, January is going to be winter, July is going to be summer. And so if we look at Texas here in the winter time like it is right now, we're getting air that's blowing over the entire continent of North America coming down from Canada, which is why generally we have dry, cold air. By the time it gets to us, it's dropped all the snow. We don't get very many snow days, which is sad. But we still get the cold weather. At least it's not as cold as like Kansas or up in Canada. But it's still pretty cold air. And then in the summertime, it's hot, moist air coming up off the Gulf of Mexico, which is why we just have hot, really humid summers. That's our general weather pattern here in Texas. So they talk about westerlies. Westerlies are going to move from the west towards the east, and I'll go ahead and take this moment to tell you that when we talk about winds, we tell you the direction the wind came from as opposed to which way it's headed. The direction it came from is more important. So like if I say there's a north wind, it's coming from the north to the south, and because it's coming from the north, I can expect it to be cold. Southern winds are going to be warm and moist because they're coming from the south. So the westerlies travel from the west to the east. In the northern hemisphere, they create anticyclonic and cyclonic flows, and they basically help kind of keep our weather a little bit mixed up and exciting in a way. Produced from temperature differences, they got small scale winds, land and sea breezes, mountain and valley breezes, and then Chinook and Santa Ana winds. So the land and sea breezes, this is like oceanfront kind of daily weather patterns, which is what helps keep our ocean areas rather nice. Why a lot of people like to live in California and in Florida. Because in the day when it's hot, you get these cool winds blowing off of the sea. Because the sea is generally cooler, it takes longer to heat up. The continent heats up faster. So you get these cool sea breezes. In the night, your continent cools down faster. The ocean is a little bit warmer, and you get these cool seaward breezes blowing from the land towards the ocean. And it kind of helps like regulate everything and keep it from having too many temperature differences there. So yeah, that's why the right on the beach areas are generally very nice day and night. Same thing with the mountains. You kind of have the same day-night pattern. In the daytime, the mountain sides heat up and your warm air rises up the mountains. Cold air drops down into the valley. In the nighttime, everything reverses. Your mountain breeze comes down off the peaks, down into the valley, and your warm air starts to rise. In both scenarios, your valley is pretty cool there. And so a similar kind of effect between your mountains and valleys. And then they have Chinook and Santa Ana winds, which don't really affect here in Texas. Chinook is obviously a Canadian word. Warm, dry winds moving down the eastern slopes of the Rockies. And then Santa Ana winds are Chinook-like winds that occur in Southern California. And so you can kind of see the Santa Ana winds coming down over here, giving them a particular weather pattern. We don't hear about them too much in Texas, but every once in a while, if you watch the weather, the weather people will kind of mention them as a part of a nationwide weather pattern. So describe the formation of a sea breeze. In the daytime, the wind is blowing off of the ocean towards the land because of temperature differences. In the nighttime, it reverses, and it blows from the land towards the water. Two basic measurements for wind. So we have wind direction and wind speed. That's what we need to know. The direction is going to be named from the direction it's blowing from. So north winds blow from the north towards the south. South winds blow from the south towards the north. And then speed is obviously important. Here's how we measure those. Has everybody seen the windsock? If you don't know, the windsock tells you both things. Obviously, it's going to point in the direction the wind's blowing. But if you think about it, the harder the wind blows, the more your sock is going to stand like straight out. So like this is a moderate wind. If it's going all the way down, your wind's not blowing very, very hard.
Following students need to report to the cafeteria. Bailey Delgado, Alien, Escobedo, Karen Escobedo, Kristen Gamble, Eric Garcia,
She's
Ami
fixing that.
Garcia, Samantha Griffin, Gavin Guerrero, Caleb Harper, Carl Harper, Nadia Harwell, Lily, Garrett Holmes, Ethan Huskins, and Ganson. Report to the cafeteria.
And Jansen?
Are they just calling people like in order of who wasn't here
I don't
during
know.
the last one?
I don't
Like,
know.
online?
Have they even done one this year?
Mm-hmm.
Yeah,
Oh,
they
have
did
they?
one at the beginning
Oh,
with everybody that was here.
yeah, I don't know.
So I guess they're doing a
Oh,
whole bunch of people that
maybe,
weren't here.
maybe.
So
Yeah.
I feel like they're
Yeah.
doing everybody that was.
I thought about it yesterday. We haven't done tornado drill or a fire drill or a lockdown drill all year. Yeah, I know. Yeah, I was thinking like you didn't want everybody to be crowded up in the same place. So yeah, it is what it is. So
Shut up and these freshmen don't know what to do.
well, you will all guide them because we've all done it plenty of times. And hopefully everybody seems more subdued with the masks on. So hopefully we won't have any. We've never had any problems, but I wonder if this year, like this school year, will be like a low in recent years for like school shootings and violence in schools.
It hasn't been so far.
Yeah, no. I wonder, someone's gonna like look into that psychologically and be like, why did the pandemic and wearing masks keep people from having as many school shootings? Or is it just that there's less students in the school?
Less students in
Uh,
school. A lot of places are still locked down.
Yeah, a lot of places are. But even the places that aren't, like I haven't heard anything happening. So there's something psychological there happening that someone will study. So over here we have more modern technology with a wind vane, which is going to tell you the direction the wind's pointing, and then a cup anerometer that's got a curved side and then a cup side. So the wind's going to blow at a certain speed and tell you how fast your wind's blowing. So old school technology, new school technology. Global distribution of precipitation. Regions influenced by high pressure are usually going to have dry conditions. If you got a low pressure system, you're going to have rain and more weather going on. Other factors that do influence precipitation, the nature of the air, how much moisture it can hold, your latitudes, because obviously higher latitudes you'll have colder temperatures, lower latitudes toward the equator you'll have warmer temperatures, and then distribution of mountains, where your mountains and your continents are. So here's your overall weather and moisture. We're not too bad. We're like in the green here, which is middling. We're not in the deserts. We're not in the tropics. So we're not too bad here. Notice Australia, rain around the outside, very dry on the inside. And then the Philippines just get rain like all the time. So very, very tropical down there in the Philippines. So yeah, this general moisture distribution kind of thing. And what is this map? This map is like all over the place. You got the like global cut. You got Australia just cut off by itself. I wonder if this is like a specific type of mapping. It's interesting to me, to my brain. So that's the end of chapter 13. Goodbye, chapter 13. Hello, chapter 14. Let me go back to the beginning. And depending on how many announcement stops we have, we might get most of the way through this. Well, we'll get most of the way through this. So now we're into weather, like actual weather and weather patterns and what we look at on weather maps. And we start with air masses. The characteristic of an air mass is it's a large body of air. It's got to be the same same temperature, same moisture. If it's different temperatures and moistures, you should call it two different air masses. Generally, air masses are very large, 1,000 miles or more across, and several kilometers thick. And how they move about affects your weather. So right now, what we have going on, not this bad, but we got a cold, dry air mass coming down over the central part of the continent, which is giving us cold temperatures. Somebody looked this up earlier. -9 Celsius is about 15 degrees Fahrenheit. So we haven't had anything that cold yet. But you want to know why? We're cursed to never have any snow days here in Texas, where if you go just a little bit far north to Oklahoma, the 2 years that I was up there, we got at least a week of snow days every single year. And one year we were closed down for like 2 weeks straight, which was great. It was just shut everything down, 2 weeks at home. It was wonderful. Down here, very little every year. Don't get a lot going on. Because by the time this whole air mass moves all the way down here, it's dropped all its snow. Winnipeg, lots of snow. South Dakota, Kansas, Omaha's Nebraska. Nebraska, Kansas, they get all kinds of snow. Oklahoma, you get snow, but not all the time. Dallas and Houston, almost never. So not very much snow. You just go an hour or two north, and you get definitely a lot more. So we're real close to the line there. In fact, how many times you see they get like snow in the Panhandle or up around the Red River, but we don't get any? Happens all the time. Or even up in Denton, like UNT will get snow and we will get nothing. Just that far further south, and we don't get anything. You can tell that I'm really like, I need a snow day this year. I need to wake up in the morning and have somebody on the news tell me you're not going to work, and that would be nice. So your weather depends on where your air is coming from. So we have two different ways that we describe that. Polar and tropical. What is polar air probably going to be temperature-wise? Cold. And then tropical is going to be warm, yeah. So polar and tropical are great descriptions. Polar is going to be cold, tropical is going to be warm. And then we have continental, maritime. Moisture-wise, continental is going to be dry. And maritime, which is like oceans and boats, is going to be wet. And so you can have cold and dry or cold and wet with polar continental, polar maritime, or hot and dry or hot and wet with tropical continental or tropical maritime. And so here's a map that kind of shows you all of them in one complete scenario. You've got maritime polar in the wintertime, keeping the Pacific Northwest nice and snowy and cold. Same thing with New England up here. But the central part of the country, cold and dry generally. Continental polar, there is plenty of snow that happens in the central part of the country, but definitely not down south. By the time it's gotten to us, it's dropped it all. In the summertime, we get more of this maritime tropical, hot, humid air that just makes the summers miserable, and you want to stay inside in the air conditioning all the time. Note the little bubble of continental tropical, like New Mexico, Arizona, is why they don't get a lot of rain there, because they're not getting this Gulf moisture or the Pacific moisture very often. Air masses and weather, they just go through some different scenarios in the United States of where we get our air masses and weather. So North America, east of the Rocky, we generally get this continental polar, which keeps everything kind of dry and cold. In a second, though, right here, they're talking about lake effect snow. This dry, cold air mass comes over the Great Lakes and picks up a bunch of moisture, which it probably shouldn't have. And so as soon as it gets a chance, it dumps it on the other side. And so you can see the amount of snow. This is snowfall. Dark blue is the most. The amount of snow in all these.
Eric Garcia, please
oh,
report to
I
the
didn't even hear a beep.
cafeteria. Eric Garcia, thank you.
Oh, just the one. All these areas just to the east of the Great Lakes get a lot of snow, including Buffalo. From what I've heard, nobody wants to live in Buffalo. It's just cold and snowy all the time. And on a side note, that's a big thing for sports teams. If you haven't noticed, not a lot of people want to live in Dallas either. When it comes to free agents for sports teams, we're like, hey, we'd love you to come here. And most of them are like, no, I'll go almost anywhere else because I don't see like Dallas is having a lot of stuff for me. So we usually have to draft people and get them to stay here as opposed to picking up huge free agent pickups. The Mavericks have a lot of problems with that, and the Rangers too. no one wants to pitch in the hot summer heat, and so all the big pitchers usually go somewhere else. So moving on. Air masses and weather, they're still talking about the different types of air masses we get and what kind of weather they bring. If they come from the maritime, they're going to bring precipitation. If they come from the continental, they're generally going to be dry, and that's going to affect your weather. They also show how air masses can change. Your continental polar coming from like Siberia is cold and dry, but as it comes out over the Pacific,
Following students need to report to
it's going to pick up moisture, so it becomes a moist, dry, or moist, cold air package.
Grayson Jarrett, Michaela Jones, Juan Lopez,
I got you.
Cassandra Martinez,
Or was it?
Joshua
Oh, your
Mitchell,
sister.
Divine Mendez, Alexis O'Connor, Christopher Ortega, Jose Ortiz Carmichael, Kenya Padron, Landon Perez, and Jose Fuentes.
Okay. So what is associated with the lake effect snow? A cold, dry air mass that comes over the Great Lakes and picks up a bunch of moisture and then immediately dumps it on the other side. That's your lake effect snow. Now we get into fronts. And we've seen this. If you ever watch the weather, you know about the fronts. They're pretty straightforward. We have warm fronts. We have cold fronts. We have stationary fronts, which don't really move. And then we have occluded fronts, which is kind of a combination of both a warm and a cold front. And so here's your warm front. How you see it on the weather map, obviously red is warm. Blue is going to be cold. Also for our, I guess, I don't know, maybe it's just for weather too. But for our colorblind people that have trouble seeing red and blue, the circles are for your warm fronts and the triangles are for your cold front. So even if it's a black and white picture, or if you have trouble seeing color, you can see that it's a warm front versus a cold front. So warm fronts have the circles. The circles point in the direction the front is moving. So the front is moving towards the right. Your warm air is still going to stay above your cold air, but it rises very slowly. So you don't get a lot of rain, just light to moderate precipitation. No big cumulonimbus clouds. The clouds just kind of stretch out. And generally it moves kind of slow, so not a very fast-moving front. You go over to a cold front, and the big deal with cold front is it has a higher angle here. So instead of like this slow wedge, it's kind of a big curve that happens. And so your warm air gets pushed up rather quickly, which forms your big cumulonimbus clouds, heavy precipitation, lightning, hail, possible tornadoes. This is the weather we see here in Texas a lot. The color, you have your blue cold front line, but instead of circles, it's triangles, and the triangles point in the direction the front is actually moving. Then we have stationary and occluded fronts. Stationary is going to follow the name. It's going to be stationary. It's not moving. Occluded fronts are when the faster cold front overtakes your warm front. So your warm front's moving that way. Your cold front's moving that way. The cold front moves faster, and it makes this kind of wedge. It's going to push all your warm air up and get a specific type of weather and storms that happen there with your occluded front. They're usually not very big, but they do happen. So here is an example in your mid-latitude cyclone. You have your cold front out here moving down, which is actually what's happening today. Your cold front sweeping through. We're going to get a little bit of storms and colder air on the backside of it. Your warm front is out in front, kind of pulling this warm air away. You have a little bitty occluded front. So occluded is a combination of cold and warm. If you take the colors from cold and warm and put them together, red and blue are going to equal purple. And instead of just the circles or just the triangles, we have circles and triangles alternating but facing in the same direction. I'm showing you the direction of the occluded front. On the back side here, we have a stationary front. So this isn't really moving. They have the alternating red and blue and the alternating arrows and circles pointing in opposite directions to tell you that it's not going one way versus the other. It's staying right where it's at. So a little bit complex on the weather patterns. Now they go through warm fronts, and they're basically hammering home. Warm fronts are not going to have a whole lot of rain, some light precipitation, and your temperatures are going to be warm on the backside because your warm winds coming through. Your cold fronts are going to have lots of rain, possible hail and tornadoes, that thick wall of dark clouds that like blows through very quickly, And on the backside, you get clear skies and lower temperatures, which is what we get quite a bit. You can't really see it too well on this, but you have a line of clouds that come down right in the front of that cold front there. And then you kind of have a break in between the cold front and the warm front. So sometimes you can spot these from satellite pictures without even really like having the weather there. And so that's what you see. This line where the clouds start is the cold front. So the cold front comes right along here, and you see the weather that's happening right in front of it. I would say the warm front probably comes down here. I don't know for certain, but probably comes down here. And then you have this wedge of kind of clear weather in between the warm front and the cold front. This would be your low pressure center, and then you probably have a high pressure center somewhere over there, kind of keeping them from having real bad weather. So here's another 3D map of what's happening. We've kind of already seen this. Air flows in towards the low pressure and heads up. Air flows out away from the high pressure and heads down. And you kind of have the opposite happening up in the upper portion of the atmosphere. Explain briefly how flow aloft aids the formation of cyclones at the surface. So as you're, well, let's see, what are they talking about here? Oh, your jet stream is going to bring air along this direction. What's happening at the top is the opposite that's happening at the surface. Where your low pressure brings air in, it's going to come up and expand at the surface. It's going to diverge at the surface and converge above the high pressure system. So it basically maintains this whole like circulation between your high and low pressure and your cyclone and anticyclone. Now we get into thunderstorms. The features of thunderstorms are your big, tall cumulonimbus clouds, your anvil head clouds as they call them. Heavy rain, lightning, occasional hail, sometimes thunderstorms. How often do they occur? About 2,000 in progress at any one time across the globe. So there's always a thunderstorm somewhere, raining on somebody. 100,000 per year in the United States, most frequently in Florida and the eastern Gulf Coast region. Here's your weather map. Florida and Georgia get a lot of thunderstorms every year. Texas, we're not too shabby. We're in the green and the yellow here, so not bad. But definitely a decent amount of thunderstorms. And notice, this is for thunderstorms. In Pacific Northwest, they get rain all the time. It's just not thunder rain. You can go outside and stand in it if you want, and you're not going to get struck by lightning. They do get thunderstorms, just not super often. Where pretty much here in Texas, if it's raining, it's thundering outside. There's not a lot of times where we get rain without thunder. Here's a lightning map. It's pretty small. Maybe I should try to blow this up for another year. But the lightning map, we got a fair amount of lightning. This like dark purple area right in the middle of the African continent, right along the equator, apparently gets the most lightning. That's like a crazy amount of lightning there. So how do thunderstorms develop? Your warm, moist air has to rise. It has to have instability and rise very quickly. That's going to build your big anvil head cumulonimbus thundercloud. There's going to be strong updrafts and downdrafts, which are going to drop all your rain out, but keep the cloud like powered up in a way with more energy from this warm, moist air coming up. So what are the basic requirements of the formation of a thunderstorm? Warm, humid air has to rise in an unstable environment to create that big thundercloud. Local storm, short duration. They're talking about tornadoes now. So tornadoes have to form from a cumulonimbus cloud. They have low pressure inside. The winds can reach up to 300 miles an hour or sometimes more. And there's a lot of dynamics in a tornado. Sometimes you can have a smaller tornado inside. You can have little parasitic tornadoes coming off the outside. On average, we have about 770 each year in the United States. Most frequently in April through June, which is tornado season, especially here in Tornado Alley. They're associated with thunderstorms. You don't ever have a tornado siren go off like when it's clear skies outside. It's got to be a thunderstorm involved. We don't really know the exact cause, but we're getting better at that. We can, you may notice now, this is not a thing when I was a kid. They're going to let you know before the day even starts. We've got a storm front coming through, and the conditions are right for tornadoes. There could possibly be tornadoes in the storm. Whether there will or not, they don't know. But it's not just like a wait and see thing now. They're starting to get better at predicting. Formation of tornadoes occur most often along that cold front where you get your really violent storms. And most of the time, they're looking for those supercells. You'll hear the weather people talk about that pretty often. Supercell thunderstorms and the possibility for tornadoes. So this is just a picture that kind of shows you as you get this updraft air, it can kind of circulate around and start to form your vortex, which could eventually spawn off a tornado. Or in the worst case scenario, 3 small tornadoes inside of a larger tornado, which seems like a movie kind of scenario. But there's crazy stuff happening inside there. There's a lot of dynamics going on. So, characteristics of tornadoes, diameters 150 to 600 meters, which is about 500 to 2,000 feet. The speed, roughly 30 miles per hour, and this is like speed on the ground, like how fast it travels.
Report to the cafeteria. Luis Ramirez, Cesar Ramos, Juan Sanchez, Jesus Salcedo, Lane Salisbury, Tanner Shadburn, Mason, Shook, Emma Tapp, Eddie Vargas, Audrey Vila, Liliana Villa, Brooke Washington, Chelsea Washington, Chelsea,
Yeah.
Matthew Weatherford, Rosalie Wilhite, Ian Williams, Brandon Yang, Dalton Ely, and Jacob Zapata Gonzalez.
Okay, so they move about 30 miles an hour. Like that's directional movement, not the rotation. They can cut a 6 mile long path. That's pretty long. Most of them drop down, hit a small area, and then go back up. But some of the bad ones can be like miles and miles long. Max winds over 500 kilometers per hour, or 310 miles per hour. Intensity measured by the Fujita intensity scale, which is your EF 1 through 5. And living around here, you might have noticed it takes them a while to know for certain what that is. They study the damage on the ground after the tornado's over and try to measure how bad the winds were blowing. They can kind of estimate beforehand, but usually it takes a little while for them to actually get that rating. So tornado forecasting, we know this because we live in this part of the country. Tornado watch tells you that it's possible. We don't know that there's a tornado. No one spotted anything going on, but the conditions are right. So maybe keep an eye out and see what's going on, and keep the TV on or keep your phone with your ringer on in case a notification comes through your weather app. Everybody has a weather app on their phone. Don't delete it. Use your weather app. It's nice. Tornado warning. We've seen a tornado. There's rotation. We've seen it come down. We've seen it touch down. So there is an actual tornado, and it could be headed your direction. So take cover. So those are 2 different things. Watch is just a heads up. A warning is an actual tornado has been spotted. Why do tornadoes have such high wind speeds? Because they're directly related to extreme low pressures. And so the lower the pressure, the more the wind's going to rush in, and it's got to go up because that's the way low pressure works. It comes in and goes up. And as it goes up, it's going to start to cycle. It's going to start to rotate. And once you get that rotation, you get the vortex and you get a tornado. So now we move on to hurricanes. This is nice. I didn't get this far with the last class, even with all the stopping. We only have a couple minutes left, but we can get close. To be called a hurricane, it's got to have 74 mile per hour winds. So we've also seen the progression from tropical depression to tropical storm, then to hurricane. And then they have the 5 different levels of hurricane. Is it 5? I think so. Anyways, we'll see in a second. They form usually between 5 degrees and 20 degree latitudes. You don't see hurricanes forming up near Canada. They come up from near the equator, not at the equator, but near it. Wind speeds reach a peak of 300 kilometers per hour, generate 50-foot waves at sea. In the western Pacific part of the world, they call them typhoons. In the Indian Ocean, they call them cyclones. not to be confused with the cyclones that we use for our weather patterns over highs and lows. But it is a similar thing, a rotation of an air mass. The North Pacific has the greatest number per year. We don't really get those hurricanes. Those usually go over towards the Philippines. We get them from the Atlantic most of the time. So here's a picture of an hurricane. We all know about the eye of the hurricane and the wall cloud on the inside there. And here's kind of a picture of what your hurricanes are doing. So most of our hurricanes we get formed come up through the Gulf and hit the southern part of the United States, sometimes up in the eastern. But if they form the other side of the Pacific, they just go the other way. They don't really head towards. You never hear about California getting hit by a hurricane. I mean, I'm sure it's happened a couple times, but not very often and not super bad. Notice there aren't really any hurricanes that cross the equator, and that's because they're headed opposite directions because of the Coriolis force. So when it does happen, they tend to fall apart really quickly because once they cross over to the other hemisphere, they want to rotate in the other direction. The Coriolis force kind of tears them apart. And so we kind of have this safe zone for hurricanes right along the equator. This is just showing you a couple different parts of hurricanes. What's our graph showing us here? Surface pressure and wind speed. This is times down here on different days. And so it's just kind of showing you that the faster your wind goes is going to be associated with that low pressure area. So as you get in towards the center of the hurricane where the pressure is the lowest, your wind speed is going to rise the most and be turning the fastest. Hurricane formation and decay, it's all about energy. As long as they're over warm waters in the ocean, they will be bringing up that energy from the warm waters and continue to get stronger and stronger. We'll finish these last couple slides tomorrow and start on the signature assignment